Hello, everybody, and welcome to We Measure the World, a podcast produced by scientists for scientists.
So if you have matrix potential, soil suction, and water content, do you even need to know anything about the soil type anymore?
You know, when it comes to understanding the hydraulic properties of soil, no. Those are the things that we need to know. Now, there are other physical properties that we probably need to understand soil type when it comes to like plasticity index and things like that. But for most people, most applications, if you know the water content and water potential and you understand that relationship, it tells you pretty much everything you need to know.
Any comments on that? Can go straight to Leo Rivera.
Or Brad. Just send them to the group.
That's a small taste of what we have in store for you today. We Measure the World explores interesting environmental research trends, how scientists are solving research issues, and what tools are helping them better understand measurements across the entire soil-plant-atmosphere continuum. Today's guests are research scientists Leo Rivera and Chris Chambers, both of whom are water content and water potential sensor and application experts here at METER Group. Chris Chambers operates as the Environment Support Manager and has been the Soil Moisture Sensor Product Manager for many years at METER Group. He specializes in ecology and plant physiology and has 15 years of experience helping researchers measure the soil-plant-atmosphere continuum. Leo Rivera operates as a research scientist and director of scientific outreach at METER Group. He earned his undergraduate and master's degree in soil science at Texas A&M University, and there his research focused on the impacts of land use and landscape on soil hydraulic properties. He also helped develop an infiltration system for measuring hydraulic conductivity used by the NRCS in Texas. Currently, Leo leads METER's collaborative research efforts and focuses on application development in hydrology instrumentation, including the Satro infiltrometer and the HyProp. He also works in R&D to explore new instrumentation for water and nutrient movement in the soil. So Leo and Chris, thank you so much for being here.
Thanks, Brad.
Thanks, Brad. Happy to be here.
All right, so we probably need to start out by talking about the differences between soil water content and soil water potential. Can you just give us a brief definition of both these parameters? What is soil water content and what is soil water potential?
Right. And so what we're talking about is ways to describe the state of water in the soil.
Yep.
And they are both extremely valuable and give you complementary information. And so the soil water content is the amount of water there. It's how much water is in any given volume of soil.
Yep.
And the water potential is the energy state. So when we talk about these things, people generally say soil moisture, and they generally mean water content.
Yep.
We're trying to get a little broader view of soil moisture out there, and it really includes both of these parameters.
Yeah. Yeah, and oftentimes, I mean, when people look at water content or water potential, they're typically linking at it in terms of volumetric water content, how much water is there per volume of soil. But geotechnical engineers often like to look at it in terms of gravimetric water content, so it often depends on the field that you're coming from and how you want to look at it. Geotechnical engineers also like to call soil water potential soil suction, and they look at it in terms of a positive value, so it's the inverse of water potential, which this takes some time. It takes a little bit to wrap your mind around that sometimes, but depends on the field you're coming from and what you're really trying to understand and how you're using that information.
Yeah, but in the end, it's the mass and the energy state.
Yep.
All right, so that being said, what types of situations would you only need soil water content, and in the same vein, what type of situations would you only need soil water potential?
Should we play our favorite game for a bit?
Sure.
Okay. Water content or water potential.
Okay.
We've done this a couple of times, so you might have seen it before. Bear with us a little bit. Okay. So let's start with maybe not as easy as you might think. Set point for irrigation control.
Ooh, good question. So ideally, we're going to control our irrigation to hit a target water potential, but we need the water content to know how much water we need to add to hit those target points.
See, we threw the curve in too early.
See.
So we'll come back to that.
Yeah.
Let's do a new one. How much tension is going to be on the water column of a plant?
Water potential.
Water potential.
All the way.
Let's say what do you want to measure if you want to measure the amount? See, I'm giving it away here. It's hard to phrase these without giving the answer in the question. The amount of water lost.
Water content's going to give us the most information there.
Right.
Yeah.
Right.
Let me throw one your way.
Mm-hmm.
If there's a risk of slope failure.
Ooh. So once again, we're back to needing both of those, right?
Yeah, I think for slope failure, the amount of water there is helpful, but the biggest factor is the water potential, or the soil suction, as engineers are going to refer to it, because that kind of gives us that intrinsic strength component.
But sometimes the positive pressure is a factor there too, right?
For sure.
Positive pore space.
Yeah, so we're ideally looking at both the negative and positive pore pressures.
Great.
Yeah.
How about freezing potential in, like, say, in like a wheat hardiness study?
Ooh, throwing a curveball in there.
Yeah.
That's a good question. Freezing potential. I think water potential is probably going to govern that more, right? But also we could use, if it's actually frozen, we can use temperature to infer the water potential.
Yeah, and they'll kind of give you the same information, right?
Yeah.
When you hit the freezing point, they're
Yep.
both going to just look like really dry soils.
Yeah. And then from there, you can use temperature to kind of infer what's happening there.
Okay.
So
As often as we play this game, you'd think we'd be better at it by now.
All right, so you have given us a couple instances here, examples of when water content and water potential work well together. So are there any other, or not are there, but can you give us some other examples or situations when it's appropriate to measure both of those parameters at the same time?
So people are really used to using water content because it's easy to understand, right? Basically, at the end of the day, you get a percent. And that's really easy for people to wrap their head around.
Yep.
You're looking at a volume of soil, that's 25% water content, volumetric water content. Then, right, about the fraction of quarter of that soil is made up of water.
yeah.
Unfortunately, it's a lot harder to interpret than many people realize, because 25% water content in a sand is more water than any plant needs, and in a clay, it's probably well beyond the permanent wilting point. So you can't really just use water content in some situations. You either need the matrix potential as well, or you need to know some more information like the soil type.
Yeah. And I think I'd even argue that in most situations where people are just using water content, they're doing it based on historical knowledge of what that means for that soil. And really it's because they've spent enough time knowing what that means in terms of water potential without knowing that they're actually trying to understand that. They're like, my plants are happy, my plants are sad. These are my set points for water content.
Especially in seasonal areas where you've got a couple years of data, you know where it peaks out in the wet season, you know where it flattens out, where the plants draw as much as they can in the dry season. If you live in a climate like that. So that's really how the context is given to a lot of water content studies.
Yeah. And one other, if you're looking for a specific application, anytime you're trying to understand hydrology and water movement in soil and where it's going, you need both parameters, because the governing factor of which way the water is going to move is the water potential. And the amount of water that we're moving is going to be based on the water content. And so anytime we're doing a hydrology study, if you're really trying to understand, the vado zone and how water moves through the soil, you need to understand both these parameters.
The soil storage, for one, and then the direction that it's going to go, which is the water potential. And that you don't need to know as much. So let me ask you this. Maybe this question might ruffle some feathers, but I'm going to put you on the spot. So if you have matrix potential, soil suction, and water content, do you even need to know anything about the soil type anymore?
When it comes to understanding the hydraulic properties of soil, no, those are the things that we need to know. Now, there are other physical properties that we probably need to understand soil type when it comes to like plasticity index and things like that. But for most people, most applications, if you know the water content and water potential and you understand that relationship, it tells you pretty much everything you need to know.
Any comments on that? Can go straight to Leo Rivera.
Or Brad. Just send them to the group.
No, yeah, okay, let's take that a step further. Okay. So now we have, and really this is a lot more of an issue because water potential, matrix potential used to be a lot harder to measure, right? Mm-hmm. I mean, how long did we spend developing the Teros 21?
How long are we still spending?
How long are we still? When is the Teros 21 going to be fully cooked?
Yeah.
But now we're pushing the measurements down, getting some reliable readings at the permanent wilting point and below. Mm-hmm. So it's that reading's a lot more accessible. Do people really know what to do with those together? Now we're kind of getting into, we can get water content and water potential pretty reasonably and make accurate soil water retention curves in the ground.
Yeah.
So how do people use that? What do we do with this extra power?
Yeah, that's a really good question. I mean, you've talked about the amount of time we spent developing these sensors, which has been challenging. And we're still continuing to push that. In order to really, we are now at a point where I think we can really utilize these tools in the field to characterize these soil hydraulic properties in a way that we haven't been able to do before, and where we've relied on laboratory methods to do that. So I think there is a lot more power in our capabilities now. Now, I will say that I think we need to keep pushing the boundaries in terms of what we can do with these sensors.
Right.
But for a lot of applications, these sensors are super powerful now.
Yeah.
With what we've worked on with these solid matrix sensors, like the Teros 21, the Gen 2 version, its capabilities are so much further than they were 20 years ago.
Yeah, exactly.
So, yeah.
Okay, let's take a step back, because I just kind of threw a new term in there and we didn't stop. Soil water retention curves.
Yep.
It's the relationship between the water content and the soil suction, right? The matrix potential. And it's my experience with making that, with collecting data and then fitting the curve to make that relationship, is it's a pretty involved process. And for a long time, it's been, kind of a specialized area of science. Mm-hmm. But now it's more and more available. So why don't you tell us a little bit more about, okay, what do we do with the soil water retention curve? Why is it so important? And
well,
how is it traditionally done?
Yeah. Well, we often refer to the soil water retention curve being the fingerprint of the soil, right? And because it's unique, every soil has its own retention curve because there's different intrinsic properties that shape how that retention curve looks and what that means. Historically, there's been a lot of different ways that we've had to make these measurements, and you can't use one device, one instrument, one tool to make the full retention curve. So in the past, we've used tools like pressure plates and filter paper method, which I'm not a big fan of. And if I hear you're using filter paper method, I will be sad. No, sorry to all my engineering friends out there. And then we have tools like the dew point techniques, like with the WP4C, that have really pushed our capabilities of understanding the dry end.
Just capture the dry end.
Yeah, of the curve. But we still need to make improvements. There's tools like hanging water columns, which are great. And one of our colleagues here in METER Group absolutely loves his hanging water column. And they are really powerful for doing certain things. But then we have tools like the high prop now that have really simplified our ability to characterize the wet end of the soil moisture release curve. And now a measurement that historically has taken several months to complete, which is why it's probably been so specialized, is it takes so much time and it's not easy to do. Can be done in a week typically,
right?
To characterize the full curve. And we now have new tools like the VSA that can help us even further understand what's happening on the dry end of the moisture release curve, which tells us a ton of information. So,
Okay, and so now we've got all the specialized equipment. Generally, the data and using the data and making that thing has been confined to its own special branch of science. But now that, like right now, we have thousands and thousands of sensors in the field together collecting data that is really parallel to that process. How does the field observations that are being collected right now, how would they compare to the lab? Are we sacrificing some data quality on those? Is the analysis a little bit trickier? Because, you have to have a range of basically water states of the soil, right? From saturated to some spread of data points to capture the variability, right? To make this curve.
Yeah.
And so, you might be waiting some months. If you're in the wet season, you might not really get much of the curve. So how do you put that together on field data?
Yeah, it takes time. That's really the final answer, is that it just, to get a proper retention curve in the field, you need a good season or a couple seasons of data sometimes.
You're going to have to go the whole range or part of the range. So do you need to get down to permanent wilting point, do you think?
It depends on what you want to know.
Good point.
Do you care? Do we care about permanent wilting point, which if you're worried about, plant stress and that type of things, I think it's good to get down there. Which that's pretty doable in most conditions, unless you're irrigating heavily, or not heavily, trying to irrigate and keep things within the hyper range, you might never hit that. So it depends on how you have your sensors installed.
Right.
And how the field practice is.
So there's still going to be times when the lab analysis is absolutely necessary, because then you control the environment. You can make the curve as broad or as small as you like, right?
Yeah. No, you can do quite a bit more in the lab and do it faster, which is the power. But there's more power in understanding what's happening in the field versus what's happening in the lab.
So I don't know if we've hit this one, but along with moisture release curves, how long does it take to make a moisture release curve in the field with in situ sensors? Yeah,
we kind of touched on it a little bit, but really, ideally, you're going to need 6 months to 9 months worth of data in most cases, because if you're really trying to get a proper retention curve in the field, you need a good wetting and drying period. And for example, we have some sensors installed on the soccer field right now, we have a soccer field that we outside of our building, just to explain that, where we have an irrigation project in place where we're trying to control based on evapotranspiration and the water content and water potential data and really fine tune our irrigation practices. I won't have a full in situ retention curve from those until probably November. And I installed those sensors a couple weeks ago, actually a week ago now. So it takes time. It also depends on your climatic conditions, what you're going to hit. But it also is, something that you need to understand is that so much release curves, we talk about wetting versus drying curves, but there's really this scanning function that happens when you're going back and forth. And that's why when, we oftentimes see people try to use one portion of the soil moisture release curve to try and understand what's happening completely in the soil. And there's risks when you do that, because wetting and drying behaviors are different. And then when you're in that scanning curve, it can be different. And that's why when you have that actual physical measurement of water potential in the soil, you know exactly what's happening. And then we can fully understand those properties and how that behaves. And anyways.
You have talked about some of the practical applications for soil moisture release curves. Are there any others that you feel like our audience would really need to know or understand about how soil moisture release curves would be able to impact or affect or help their research and their studies?
And not just research for this, because there's a lot of and this is where we're kind of on the cusp of, making these data making these data presentable and presenting it in a way where people can absorb the information from the soil water retention curve and make decisions on it. And there's a lot of really interesting possibilities coming up. A few years ago, how long was it when we had the big floods?
Oh, yeah.
Just right around the Palouse here.
That was probably 4 years ago now.
4 years? Oh,
yeah.
Gosh. It doesn't seem that long ago.
Yeah.
But as a sensor company, you can imagine, we install stuff all over the place. And just to see, well, how is this going to react here and there? Yep. So when we had a torrent of rain just over a short span of time, I can't remember, it was over a couple of days.
Yeah, it was less than a week for sure.
And but it wasn't an insane amount of rain. We've gotten that much precipitation before without flooding, and in this particular case, all of downtown Pullman flooded. There was flooding all across this region, Moscow, and we went back and looked at some of our sensor data across the region. And what was interesting is that we could see that in this case, we'd had a freeze. A lot of the pore spaces had filled up. And the different part about this was that there was no place for the water to infiltrate into the ground. And if we didn't have both tension to realize that, hey, we're at saturation, and the water content for how much water was in the pore spaces, that there was a large volume of water there. We also had some stream depth sensors around, and looking back, it was easy to see that, oh, of course this is going to flood if we get this much more precipitation.
Yeah.
And so that's an area where not just the soil water retention curve, but the soil water retention curve plus some stream depth and some precipitation, and we can start making really good models without having to do extensive soil type classifications to be able to predict this kind of event. But getting that information in a consumable form is kind of the trick at this stage.
Yeah. It was funny when this was all happening, when the floods were starting to occur, we were all nerding out looking
Everybody
at the
was
data.
looking at the data.
Yeah. And but what's really, when you go back and look at it, if you look at the storage that was occurring in the soil and how you could actually see the profile filling, and we saw that in both the water content and water potential data, where we were approaching saturation at deeper depths and it was moving its way up to the surface, that it was like, oh yeah, there's not much storage capacity left in the soil, and now we have a much greater risk of flood. And then we got more rain and we had flooding.
Right.
And so that's, I think we're seeing more of this. We're seeing more adoption of soil moisture sensors and things like that, and water and water potential too in these big weather networks now, because they're starting to see that this is an important parameter for understanding things like this, and also understanding other weather dynamics. And so I'm really excited to see the future of where that goes and how they start utilizing that information. And when we start getting these big networks of water content and water potential out there, it's going to unlock so much.
It's with the irrigation potential to precisely manage irrigation. It's really kind of the simplest way to set your irrigation set points based off of matrix potential, right? Yeah. But then with other factors like the VPD, you've got your refill points with matrix potential, and then you have how much water is stored in the soil with water content.
Yeah.
So you can calculate with a few estimates of ET how long it's going to be before you hit your refill point and how much water you'll need to add precisely. So the soil water retention curves can be extremely valuable in that type of application as well.
Yeah. And Brad, to add one more to that, list of areas that retention curves are starting to bring a lot more power. We're seeing on the geotechnical engineering side of things, and what we've learned from the drying characteristics of the soil moisture release curve, that not only can we use it to understand, plant stress and things like that, and potential for flooding, but also soil mechanical properties and properties about the clay, the type of clay that's in the soil, the cation exchange capacity, the specific surface area. Like there's all these properties that all of that information is actually in the retention curve. And combining that with a few other things is really going to unlock a lot of things in terms of simplifying the way we characterize soils for engineering purposes as well. And there's researchers like Ninglu, Bill Lykos, and others that are doing some really awesome work in this area and putting a lot of papers out and working on new methodology to simplify these tests that sometimes also, again, take time, take weeks, take months to collect data on, and being able to do all of that with one curve that takes less than 24 hours to get, it's going to be so cool.
All right. Anything else you want to add about soil moisture release curves that you feel we didn't touch on?
No. Go out and measure your soil moisture release curves. They're fun.
Or just think about the way that the water state in your soil develops over time, right? And you're going to have inputs and outputs. But these two variables are, just to kind of bring back what we've been talking about, these two variables are the state of your water. And so if you can pay some attention to the fluxes, the precipitation, the evapotranspiration, then the model of how the water behaves in your soil is going to be more complete.
Yeah. And I'll just add that, historically, I understand why people have steered away from making some of these measurements, especially water potential, because it's involved tools that took a lot of maintenance, were not easy to use.
And minus 20 kPa is a little bit trickier to understand than 20% VWC.
For sure. Yeah, and water potential is still one of the hardest things to teach in soil science. Like it's the thing that takes the longest time for people to comprehend. But once they do, they see like, oh wow, this is such a powerful parameter. And now we're working, the tools are getting easier to use. They're getting better. They're getting more accurate, more reliable. And so hopefully it's going to make it easier to adopt. And as we work on making them easier to install, the hope is that these are going to become more powerful tools for your more general users of this information. And so that's, we're going to keep working on that and trying to make the tools better. But it's really fun to see what people are doing with it.
With everything that you guys have been saying about water potential, and we feel and believe and understand it to be so critical, why does it seem like we're just now starting to talk about it so much versus, compared to water content, which has, been around forever?
It's a good question. I think some of it has to do with the tools, like just how challenging it has been to measure them. But I also think, if we think about, let's just use the food industry as an example, and water activity, which is the same thing it's the same as water potential, just a different way of looking at it in food. And what they've learned is that water activity tells us so much more about what actually is going to happen with that food product. Is the risk for mold, risk for bacteria, how it affects the texture and taste of the food. And it took them a long time to move away from water content measurements of food to water activity. And sometimes it takes a long time to change mindsets. And some of it is that, again, water potential has been so hard to understand. Like, of course they're going to be scared of it.
Let me throw this out there. Let me challenge you with this, though, because is it just the accessibility of the information? Because sometimes you can, if you've got matrix potential, and this came up last year. I was just, I wanted to learn about some set points for growing tomatoes. You dig into the literature, and it's like, you want it at minus 20 kPa for this part of its development cycle and minus 40 kPa for this part of its development cycle. There's a lot of information like that that's already been done, research that's already available. Yeah. Is it just not getting to the right places? And if not, how do we get that message out further?
That's a good question. If you were to ask somebody, just let's say somebody called you up on the phone, and you ask them, "Hey, do you know what your target water potential ranges are for your tomatoes?" Would they know the answer to that
right now? I guess not. But that information's there. It's been done.
Yeah, it's there. But how accessible is it? And how this is in research. This is the challenge between research and getting that information in front of general users, which is
Yeah.
oftentimes the role of like extension groups and things like that. And I think that's where we've maybe missed the mark a little bit is, there's a ton of, we see this in other industries too, where people are trying to repeat work that was done in another industry 30 years ago.
Yep.
But that information either is not easy to find or they just didn't take the time to find it, of course.
Right.
But yeah, it's just, I think it's up to us as we educate, not just ourselves, but other folks that are teaching these things that there is this information out there, and you have to get it out there. Now you'll find those niche people who like dig through Google and find this information, but how many people actually do that?
I don't know.
All right, and so in this instance, then, if we have people, if it's an issue with getting that information out there, or adoption of this information, how would you then explain water potential to a colleague or somebody who has already used water content and then doesn't see the need to use anything beyond that?
Yeah, that's a good question. And there's the first thing that comes to mind for me is it's great if you know what your water content means at that spot in the field. Can you apply it to another area if you move to another field? Or the thing is, we know that these properties are these, we're seeing the term a lot now, dynamic soil properties change around. So as practices change on the land, as land use changes, or as we start, improving our growing practices, whatever, like starting to move towards no tillage or other things, these dynamic soil properties, which the moisture release curve is a dynamic soil property, change. So what you thought the water content meant a while back doesn't mean the same thing as these properties change. And so, like if you really want to understand what's going on, you need to understand these values. And when we see this all the time, with people who think, oh yeah, I'm doing great, my turf's looking good, my potatoes are looking good, and then when you actually look at what they're measuring in terms of water potential or water content, they're either way over irrigating, so they're wasting water, risking more chances for disease, or in like turf areas where these invasive species can compete better if it's too wet. There's just a lot of things where if you actually were measuring and knew what was going on, you could still improve your practices, even though you think you know it so well.
As we come to the close of this episode, is there anything else that you feel like we need to cover or hit when it comes to water potential, water content, or soil moisture release curves? Any final thoughts?
I think at this stage it's a game of communication, right? We actually know a lot about how to build these and how to collect the data, and we're getting better at making the data available. It's the putting the information into contact where people can make the decisions based off of the information, or pull it all together in one place and be able to add the context for either decision making or understanding the other variables in the process. So that's where it falls for me, and I hope we've got plans to work on that over the future, and hope to make that easier for people.
Yeah, I think that about sums it up. I mean, we need to make this information easier to understand, easier to digest, and continue to make these tools easier to use.
All right. Well, our time is up for today. Thank you again, Leo and Chris, for taking time to share your insights with us and everybody in the audience here. Stay safe, and we'll see you next time on We Measure the World.